diselenide to Se2. And we look into its bulk and interface properties in an unlocked configuration to then move into the effects of sodium doping in this material. And we will highlight two significant discoveries we made in this material when we dope it with sodium. We then are going to be able to talk about perspectives in fundamental science and an ongoing project, national project, working on this. And if we have time, we look into some technological innovations that are very relevant for the future of the technology. And on this front, we are working on 3 different projects that are actually closely interconnected. But the bulk of my research, or my talk, will be about this background knowledge that corresponds to about 10 years of research. So, CIGS, solar cell technology, belongs to the 2nd generation PV, also known as thin film. Here we see a structure of a solar cell. We start from a molybdenum coated substrate, on top of which we grow the CIGS material. The CIGS material is a p-type semiconductor, and we couple it with a very thin layer of n-type semiconductor that, together with the p-type, makes the p-n junction the core of the solar cell. And on top of everything, we have a thin conductive oxide that acts as the front contact, the window layer that lets the light through, but at the same time, it enables to collect to generate electrons. Here is a brief overview of the historical progress of the technology. We can identify some milestones, for example, the gallium alloying, and then people started to engineer the distribution of gallium through the depth of the film to minimize recombination in the back interface. And this happened in 1993. And the very same year, another serendipitous discovery was made. People realized that by growing the material on glass, they were able to improve the performance enormously. And later on, people started to introduce heavier alkali metals, potassium, rubidium, and cesium, and this pushed the efficiency of the technology up to 23%. That is just 10% absolute away from the maximum Shockley Quasar limit that's ever achievable with a single junction solar cell. So whenever we have absorption of a photon of a perfect energy in the CIGS, we have generation of an electron and a hole pair. And whenever we have electron hole pairs, there is a high chance for them to recombine. And if we look at the microstructure, it's a real wonder that this material works at all. You look at this, we have small grains, we have high surface to volume ratio, high density of extended defects, great boundaries, and surfaces. So one of the main reasons it worked at all is thanks to the sodium itself, and we look into why this is the case. But of course, we can grow the material sodium-free, and we do this in order to understand the properties of the material on its own. So we will first look into that before dealing with the sodium doping. Looking at the bulk properties of the material, we can derive CIGS, operating by selenide, by isoelectronic substitution from the diamond structure of silicon. So if we substitute silicon with gallium and arsenic, or zinc and selenium, we get isoelectronic substitution, and we, of course, we decrease the space group symmetry, but we get the same number of valence electrons. Now, imagine we have the zinc selenide spinel structure. You now replace the zinc atoms with half of them copper and half indium. You double the unit cell, and we get copper-indium diselenide structure, which is shown here. Now, every atom in this structure retains the tetrahedral coordination typical for the diamond structure, and here we see a selenium atom coordinated by 2 copper atoms and 2 indium atoms. The very same structure also holds for the copper-indium gallium diselenide, so we can replace indium with gallium in a complete miscibility range. And this is important technologically speaking, because the 2 end members, copper-indium diselenide and copper-gallium diselenide, they have a band gap that matches precisely the highest efficiency Shockley Quasar limit for double junction configuration. So in a double junction configuration, in principle, we could couple 2 absorber layers, one on top of each other, to harvest better the solar radiation and reach, imagine, a 45% efficiency, power conversion efficiency in principle. So if we learn how to make the material better, we can aim to get there. But first, we should look into the ternary system, and now I'm going to show you pseudo-binary indium selenide copper selenide section, but the same also holds for the gallium selenide copper selenide section. And you see there is a quite wide homogeneity region in the copper poor side, whereas in the copper rich side we are limited by stoichiometry. So we can grow the material within this range, and if we do that, depending on the relative concentration of copper and indium, we get to very different microstructures and different properties of the material. If you grow the material copper poor, we end up with very small grains, you see. As we move to the copper rich, we get larger grains. Now we can also probe the electronic properties of this material by photoluminescence spectroscopy, and we see here the signature of these two cases, extreme cases. Copper poor, you see, has a very broad luminescence emission compared to the copper rich. It has more defined patterns. So we see from these two evidence, we would conclude that the copper rich material should be a better material to make solar cells. It has larger grains, it has a better luminescence signature, but this is not the case. So what is going on? We have to look into also secondary phases. Of course, when you grow the material copper poor or copper rich, you may end up with secondary phases at the very boundaries. For the copper poor case, this is not a big deal because the order different compound, the beta phase that you see here, it grows topotoxically of the copper in the selenide, and it doesn't have nasty properties from an electronic point of view. But the copper rich phase, the copper selenide that forms when you grow copper rich, that is a killer because the copper selenide is a conductive phase. So whenever you have a copper selenide, unless you remove it, you don't get any working devices. The thing is, it's not the main reason why the copper-rich material doesn't work well, because if we do remove the copper selenide, we still get working devices, but they are not as good as the copper poor. So what is going on? This is a puzzling conundrum that kept the community studying for quite some time, and we had to unravel. We looked into electrochemical photocarbon spectroscopy as a technique to try to understand what is going on. So in this technique, we immersed the absorber into an electrolyte solution containing a redox couple, and we then record the current flowing to the system through a potential stud when we turn the light on. So as we move to the copper poor conditions, we get a transient such as this with a spike. Now I'm not going to talk about the spike. This is something that was known for long in the literature, but what we see here effectively, it's a current, a photocurrent that is due to a collection of photogenerated electrons by the European 2+ redox coupling solution. As we move the material decomposition towards stoichiometry, we can start to observe a change in the transient quite remarkably. As we go to the copper rich, of course after removing the secondary phase copper selenide, we get sort of transient. It's completely different. There is no way we can understand this sort of transient unless we assume that we have generated a bulk trap. So a defect, we have generated a new defect at room temperature that is not at the surface but it's slightly beneath the surface. So what is the origin of this bulk trap? We decided to perform some simple experiment, just exposing these films to air and see what happens. So if we expose a copper poor film to air, this generally always leads to a poorer performance. But what happens now if we expose the copper-rich film that was previously etched with potassium cyanide to air? What we observe initially, it's an improvement of the performance, and then a drop. So clearly oxygen is doing something, and this defect that we have generated has an affinity to oxygen. So in 2006, Nasini and Se2 predicted that there could be the existence of a divacancy complex composed of a copper vacancy and selenium vacancy. And what we think is happening now, that we generated this double defect, and by exposing the films to air, we are passivating the selenium vacancy with oxygen, forming neutral oxygen-oxygen defect that are then basically destroying, annihilating this divacancy complex that is known to be detrimental. So what we learn from this is different chemistry impacts greatly on processor activity and performance of interfaces. So let's now look into what sodium does at interfaces. And I'm showing you here an autoprobe tomography 3D map reconstruction of the location of sodium atoms in a CIG spin. What we observe here, there is a strong accumulation of sodium at specific locations. What you see there, they are basically extended effects, great boundaries and surfaces. Given this start, what does the sodium do at such interfaces at great boundaries? Well, this is a spoiler. there it catalyzes oxygen absorption and also desorption. As we have seen this from secondary ion mass spectrometer imaging, we have performed this experiment where that clearly demonstrates that oxygen is not just physisorbed, but it is chemisorbed and it is associated with sodium. Now we expose this film to vacuum and see what happens. What happens, we have a drop of the concentration of oxygen. It's more clearly seen here. It's not very convincing because we are just looking at the surface. Then we perform the depth profiling, secondary ion mass spectrometry depth profiling, and what we observe is that the oxygen goes down to 0.5 micron below the surface, thanks to the sodium activity. And remarkably, this process is reversible. If we expose the film to vacuum, oxygen is sucked away from as much as 0.5 micrometer below the surface. What are the implications for the ultrafiltration properties? We have performed cathodoluminescence measurements. I'm just going to focus on this image here. And on the left side, on the left half of it, you see the situation of the film exposed to air. The other half of the image corresponds to the very same location recorded after 96 hours, if not 75 hours of vacuum. Okay, very same location. In an undoped film, nothing changes. What happens now with the sodium doped film? We see a remarkable change. In the very same location, the properties of the material improve. This parameter, the lower the parameter, the better the performance. We also perform Kelvin probe force microscopy measurements to assess what is the variation of the work function of the surface as a function of time during exposure to air. Again, nothing changes over a time frame of hours. My colleague got crazy doing this experiment in the very same location for 20 hours. But what happens now with the sodium doped case? We clearly see a variation of the work function over a time frame of 20 hours. This is not something physical, it's a chemical. So all these results support our hypothesis that exposure of CIGS films to air is detrimental if we don't have any sodium, because you end up forming indium oxide, and it's an irreversible process. But if we have the oxygen and the sodium in it, then we can first of all passivate this film vacancy by forming oxygen selenium, and if we are putting an excess of oxygen, well then sodium is acting as a sacrificial getter, and it forms sodium oxide phases. There are death product phases that we know, and some of these can be reverted back if we put into vacuum films. So we're now going to look back into the bulk properties, because we have to highlight one important feature of this material. We've seen we grow the material copper poor, and this gives the best performance. But if you grow the material copper poor, there is an important consequence. We are deviating from stoichiometry. That means we have tons of defects, point defects, to compensate for deviation. Specifically, what we have is vacancy of copper acceptors and indium copper donors. And these are point charge defects. And if they are not distributed equally within our material, what we end up with electrostatic potential fluctuations that are nothing but a distortion of the band structure of the material. You may wonder if this has a consequence or not for the technology. It does. Because what happens now, the bandgap of the material is dead, officially. But effectively, it's as if we had a smaller bandgap, because the photogenerated charge carriers perceive a smaller bandgap. And since the open circuit voltage of the device is proportional to the bandgap, what we end up, effectively, it's a drop of efficiency when we make devices. This has consequences also in the optical signature of the material. Effectively speaking, we don't get a step function, but we have a broadening of the absorption offset known as Urbach tailing. And we also have, if we compare the first derivative of the absorption offset with the photoluminescence the peak of the photoluminescence emission, we have a redshift of this perspective. And now, I'm going to move this one dot towards the copper poor and see what happens now there. The extent of fluctuations increases because we are increasing compensation. So the more poor we get, the more this compensation is detrimental for the device performance. The more we go to the copper-rich configuration, the better would be ideally the performance of the device. So what does sodium do effectively in the grain, within the grains? Here I'm going to show you secondary ion mass spectrometry depth profiling of the gallium distributions of the depth of the film for different diffusion experiments. The first one is a simple undoped copper-indium gallium diselenide polycrystalline film. We naturally tend to get some gallium accumulation at the back. We're not going to comment on that. What happens now if I add sodium to the system? We get a steeper gradient of gallium distribution. This is known for 20 years, and the community actually came up with a satisfactory explanation as to why this is the case, because diffusion of indium and gallium goes to copper vacancies, and presumably what sodium does when it gets incorporated, it forms sodium and copper, so it basically clogs the vacancies, so you have less possibility for indium and gallium to diffuse. Fair enough. But we know the situation is this in terms of sodium distribution within the material. And in the polycrystalline case, we have made grain boundaries. So maybe what we're seeing here is a blocking phenomenon caused by sodium at the grain boundaries. So in order to unravel this mystery, we decided to perform an alternative diffusion experiment. We performed a diffusion couple experiment starting from a grain boundary-free configuration. So we grew a copper-indium diselenide epitaxial film on top of a gallium arsenide wafer and observed what happens in terms of distribution of gallium. So this is what we have. And what we have when we add the sodium, surprisingly, it's the opposite effect of what was known for 20 years in the polycrystalline case. So initially we were very tempted to say, yes, it's a question of grain boundaries. But in fact, more complex experiment turned out to tell us it's not the case. It's not a question of grain boundaries or not. It's a question of how much copper and sodium you have. If you have a lot of copper vacancies, whenever you add a little bit of sodium, this helps indium and gallium to interdiffuse. But if you add too much sodium, or you don't have enough copper vacancies, then sodium hinders interdiffusion of indium and gallium. In the same, let's say, rationale that was proposed 20 years ago. So sodium effectively can enhance interdiffusion of indium and gallium under certain conditions. And why? How? So whenever we have a diffusion of an atom from one location to another in a crystal structure, we have an associated energy barrier. So my proposal is that if we accept the idea that sodium can enter the lattice of CIGS as a sodium and copper, but also as a tetrahedral, in a tetrahedral site, we may acknowledge the possibility for a the bonding environment of a selenium atom with a neighboring gallium that tends to try to migrate, to diffuse, to be altered. So if we alter the bonding environment, then we may have a lowering of the diffusion barrier. So effectively what I'm talking about here is that we are introducing a new theory of doping-induced diffusion catalysis in the solid state. So we asked collaborators in Finland to help us test this hypothesis, at least computationally, and the DFT analysis they performed is at least supportive of this hypothesis. So my conclusion from all this is that sodium effectively is good in CIGS. It helps to improve the performance because it reduces the extent of electrostatic potential fluctuations by easing the diffusion of point charge defects within the material. So we are now trying to study the bonding of CIGS from a chemical point of view to, in the future, hopefully unravel what is happening in the transition state, this catalytic step. So we can consider describe the CIGS with two different models, of course. A model that satisfactorily, let's say, describes the physical properties of CIGS, a covalent model. However, what we have is inconsistent formal charges. On the other hand, we can go for a wrong model. It's not an ionic compound CIGS, but if we do consider that, we get at least consistent formal charges. So where's the truth? Hopefully, luckily, my colleague, Ricardo Ficero, is helping us unravel this through quantum computational methods, and with the quantum theory of atoms in molecule algorithms, is able to tell us the atomic volumes and effective charges of all the atoms in the CIGS, and through a second algorithm, called electron localizability indicator, is able to give us electronic correlation and electron localizability information that basically produces such wonderful images that is the first ever image of a chemical bond between the selenium and an indium atom, or between a selenium and a copper atom. Now, by crossing these two information together, we also can estimate, quantify how much of a ionic versus covalent character these two bonds correspond to. And we see that selenium copper is much more ionic than the selenium. So to conclude, the effect chemistry greatly impacts interface reactivity and performance. Selenium vacancies in CIGS can form even at room temperature. Sodium improves surfaces and gray patterns by catalyzing oxygenation of selenium vacancies and dissolption of excess oxygen, sparing irreversible indium sequestration. It was assumed for decades that sodium hinders indium granule diffusion in CIGS. This assumption is simply wrong. The effect crucially depends on the relative proportion of copper and sodium. We coin the concept of atomic diffusion catalysis to account for the exotic phenomenon that is likely at the basis of EPF's reduction in CIGS. Fundamental perspectives. If sodium truly diffuses through the front-ward turbo mechanism, a number of unsettled phenomena start to finally make sense. We introduce now the idea of anisotropy-induced fluctuations in CIGS to be further explored. If you are interested, you can read this recent paper, and we are working now on this national project together with the University of Parma and CNR in Parma to unravel these aspects. We may also seek to deliberately engineer point distribution in chalcogenides in general, not just CIGS, to level off electrostatic potential fluctuations through doping-induced diffusion catalysis. I would very much like to continue working on this, talking about this. I'm not sure if I have time. Maybe I will briefly mention these perspectives of innovation from a technological point of view because are important for the technology. We focused on fundamental science, but in fact, we know one weakness of the CIGS is the scarcity of indium gallium. So we are trying with these three parallel projects to overcome this drawback by devising new complex architecture that, on the other hand, require greener fabrication routes. So we are working on this in this pathfinder project that I am coordinator of. And with this, I would like to thank the people involved in this project, of course, very much you for listening, and my beloved team members. Thank you very much.
Diego. Congratulazioni.
Vorrei dire due parole relativamente a questo premio Nasini, che quest'anno è stato particolarmente particolare, quindi è particolarmente è stato per il comitato. Vorrei anche dirvi che chi è stato attento avrà visto che abbiamo cambiato leggermente le modalità del bando, e questo devo dire che ci ha permesso di andare a fondo, no? del lavoro dei candidati, di esplorarlo in dettaglio, e la relazione che Diego ci ha fatto ci ha confortato moltissimo abbiamo certamente